Binary search trees are one of the most useful kinds of binary trees. Let's begin with two definitions. First, an iterative one. A binary search tree is a binary tree in which the value in each node is greater than all the values in the left subtree and less than all the values in the right subtree. The recursive definition requires two cases. The base case states that an empty tree is a binary search tree. For non-empty trees, there are two requirements. First, that the value in the root node is greater than the values in the left subtree and less than all the values in the right subtree. And the recursive part of the definition states that both subtrees are binary search trees. These two definitions are equivalent in much the same way that programs can be written either iteratively or recursively. Data structures can often be defined in both ways. Now that we've defined this data structure, let's consider some of its properties and how it can be used. A binary search tree is an inherently sorted data structure. We see that from the part of the definition that requires nodes on the left to be less and those on the right to be greater. Performing an in-order tree traversal produces the values in ascending sorted order. This fact is useful when we consider how to implement an iterator for the tree. Because it is a sorted structure, it must contain elements that implement the comparable interface. We saw a similar requirement for sorted collections and lists. A binary search tree can be used to implement a sorted set or a sorted map. We will use it to create a sorted set data structure in one of our examples. The Java Collection Framework does something similar. However, it uses a more specialized kind of binary search tree that we will examine later. Let's consider the three primary operations next. The first of them is the add operation. A find is done first to determine whether the value is already in the tree. If it is rejected as a duplicate. Recall that the definition stated that what was on the left must be less, not less than or equal. There is a similar requirement on the right. If it is not found, the find operation will also assist us in knowing where it should be added. Removing a value is a bit more complicated. It requires various cases depending upon how many children the node that needs to be removed contains. The leaf node is the simplest. The case where a node has two children is the most complicated. The third operation, contains, is the one that determines whether a value is in the tree. To make that determination, only one branch of the tree needs to be examined. Because the add method uses the contains method, we begin with contains. It is passed the element to find and returns whether the element was found. In other words, whether the binary search tree contains the element. Two instance variables, parent and child, are initialized at the beginning. They form a two-node window similar to the previous and current pair that we used with linked lists. Parent is initialized to null. The importance of maintaining this two-node window will be apparent once we examine the add method. Then child is initialized to the root of the tree. The search involves a loop that continues until either it is found or we reach the end of the branch. In this example, we are searching for 34. The value in child is 28, so we have not yet found it. Parent is assigned to child, so the two-node window momentarily collapses. 34 is not less than 28, so this condition is also false. 34 is greater than 28, so this condition is true, and child moves to the right. More nodes remain along this branch, so the loop continues. The current value in child is 52, so we have not yet found a match. Again, parent is assigned to child. 34 is less than 52, so this condition is true. So child moves to its left child. Child is not null, so the loop continues. Now child contains 34, which is the value we were searching for. So true is returned to indicate that this value is in the tree. Next, we examine the add method that makes use of contains. It has passed the value to add, and it returns whether it succeeded. It will only fail if the value is already in the tree. We are assuming the 38 is the value to be inserted. So when contains is called, it returns false, which means that add can proceed. Recall that in addition to indicating whether it was found, it also leaves behind values in parent and child. Because it was not found, it meant that the loop condition that tested whether child was not null failed, meaning child is null. That underscores why it is important to keep the additional reference to parent that add will need. So a new node is allocated, and the value in the element is set to the data portion of that node. The only time parent will be null is when the tree was empty prior to this add, which is not true in this example. Next, the value of element is compared to the data in the parent node to determine whether the new node should become the left child or right child. Because 38 is less than 41, this condition is true. So the new node containing 38 becomes the left child of parent. And true is returned to indicate that this operation succeeded. Finally, let's consider the remove method. As was true in both other methods, it has passed the value to remove and returns whether the removal succeeds. Like add, it first calls contains, which serves a dual purpose. It checks whether the element is in the tree. If not, remove fails. It also leaves behind the parent and child pair of references. In our example, we are asking to remove 41, which is in the tree, so contains returns true. The only time the child will be equal to root is when there is only one node in the tree, so after its removal, the tree will become empty, which is not the case in this example. Next, the check is made whether child is the left or right child of parent. In this case, it is not the left child, so it must be the right child. Most of the complexity of this operation is actually contained in the delete node method. There are three cases. The first is when child is a leaf node. It has no children. The second, that is the simplest case, and the one we are illustrating here. In this case, delete node returns a null, which has the effect of removing the leaf node. Because it succeeded, true is returned. The other two cases are when child has one child and when it has two children. If it has one child, delete node will return its child. The most complicated case is when child has two children. Okay, so we'll switch to the interactive data structures visualization to see some examples of all three operations, and most importantly, all three cases of the remove operation. All right, so first I'm going to insert a 62, and I currently have this in the mode where I need to single step through it. So notice at each step it moves down the tree, and then it's making the decision, should it go left or should it go right. So it's searching for 62, so it needs to go left, and in this case it needs to go right, and then it needs to go left, and then finally it finds it. Okay, so next let's do an insert. Now insert is also going to make use of the find operation. So it's going to go down the path where it would expect to find it, and it would expect it to be the right child of 65, but because it's not there, it adds it there. Okay, so now we'll go through the three different cases of the remove, which in this case I call delete. So we'll begin with the case which is a leaf node, so no children, so that's the 11. So it will locate that node, and being that it's a leaf node, it just removes it. So next let's do the delete of a node that has one child. So I'll pick 28 for that. It locates 28, and what it will do is it'll remove that node, and since there's only one subtree, which is the right subtree, it'll simply move that subtree up. Alright, the most complicated case now is the case where there are two children. So 52 will be the one that I'm going to choose in that case. Now what it's going to do here is it's going to look for the value that is immediately greater than 52. So notice what it drew there was it went to the right subtree, then all the way down the leftmost branch. And what it did then was move that value up into the root. Okay, so that goes through all of the various cases. The code that we examined for all three operations used iteration. Although we don't plan to show the equivalent recursive code, let's instead just make some comparisons. First, let's summarize what we already observed with the iterative implementation. The contains operation needed to maintain a two-node window consisting of a parent and child, because both the add and remove methods call that method and need the pair. A special case was needed in the add method when the first node was added to the tree, and a special case was also needed in the remove method when the last node was removed. The reason was that in both cases the instance variable root needed to be changed. Next, let's see what would be different had we chosen to use recursion. As is so often the case, helper methods would be needed to start the recursion. But the special case at the root would no longer be needed. Finally, the recursive implementation would be simpler because work can be done backing out. The need for maintaining the parent and child pair would no longer be required. To conclude our discussion of binary search trees, as we have with most data structures, we'll summarize the efficiency of the operations. There are three cases we need to consider. The best case is when the tree is full. In that case, there is a logarithmic relationship between the height of the tree and the number of nodes. That is important because in every operation we explore only one branch of the tree, whose length is the height of the tree. The worst case is when the tree degenerates into a list. This occurs if the values are in sorted order, either ascending or descending, when they are added to the tree. In this case, the height and the number of nodes are essentially equal. The average case is somewhere between the two. So let's see how this translates into the big O for each operation. The contains method explores at most one branch of the tree. So in the best case, it is logarithmic, but in the worst, it is linear. The add method calls contains. The only added work is to add the node, which is constant, so the total is the same as the contains method. The remove method also calls contains. The added work is greatest when a node with two children is removed. In that case, at most one branch is explored. So again, its big O values are the same as the previous ones. We will see later how to improve the worst case.